would like to invite Dr. Jim and Dr. Diane to come to the table to answer the questions. And we have about 22 minutes to the questions and the end of the day work. Okay, the questions, please. Who would like to make a question? Microphone.
Hello. Thank you very much, Lady, for your presentation. Bate knew that he was going to do this presentation just when he arrived here because of different situations, and he did really a very nice presentation. He shows the situation of developing countries, and one of our main objectives is to try really to do something in the South Atlantic, and it's important to have this cooperation between Africans and Latin American countries, and of course to have a kind of international cooperation and count with the International Seabed Authority. So you said the real thing. Thank you very much. I'm not going to make questions about the marine mineral resource of Senegal. Maybe in a few years I will make some questions about that. And now I just would like to make a question to Mr. Jin Kai. China is one of the contractors of the International Seabed Authority, and you are working since a couple of years in nodules. When do you think China will be able to go to the exploitation phase of this? I know it's a hard question, but we know that China needs a lot of mineral resource, a lot of metals, and I suppose you are working hard to get them.
Thank you for your question. I'm sure that one day we will go to the exploitation stage. But right now, I think that we are not consider that the exact what time, because for our consideration, we need another stage to establish some ventures. I just showed that for cameras and working guidelines for establish a new venture in appropriate time. I think this appropriate time means that when we can predict, so when the commercial time, then maybe we will go to this stage. I think it's still far away. And at the same time, that many my colleagues believe that for the mineral resources in the seabed, maybe other resources even earlier to enter to the mining stage. At the same time, for the same mineral resources, for instance, for sulfide, then it's quite clear that the activities for the commercial exploitation will come earlier in the national jurisdiction area than the international seabed area. So why I said that this is the mutual connection between the national and the international activities.
Okay, so thank you. What I would like to add is, if you're looking in Africa, the national jurisdiction, you will see happening in Nigeria, all the oil exploitation, the same in Angola. When you look at diamond, in Namibia, in South Africa, in Sierra Leone, and many other examples can be said. But getting to deep seabed mining, no tentative yet today. Thank you.
Okay. Okay. Basta. Any questions? Any questions? Okay. There.
Dr. Jean, thank you for your talk. My name is Lucia Campos. I was quite impressed when you were talking about the Chinese program that you pay a lot of attention to environmental issues and biodiversity. I know this is a forum for mineral resources discussion, but when you do these studies, you are also looking into biodiversity and bioprospection, or the potential for bioprospection as well, or not? Not in your programs.
Try to catch your question. That you mean that we pay attention about the biodiversity, yes, protection, or?
No, as the potential for prospection of biodiversity. Oh yes, of using organisms for looking at pharmaceuticals or things like that. Bioprospection.
Yeah, I think that at this moment we lack of some such ability to take the sample.
But you look at the potential. That's my
yes,
question.
we look into potential. So why we designed such a HOV, that something like that. But at this moment we pay much attention about the plan for no, not mineral resource. The mineral resource we pay periodically of the exploration of the mineral resource. At the same time, we have a plan to collect, some baseline data and also biodiversity. And as I said, without knowledge about these issues, we could not make the resources assessment and also effectiveness of the technology.
Thank you.
Hi, my name is Ange Didier Couton. I'm from Ivory Coast, geologist. So I have a question to Mr. Professor Bedidien. First, I want to say congratulations for your presentation. I know that for the previous program, you were not in the program, and after we see your name in the program, so we think that your presentation was made very later, but it was very nice, very good. Thank you for that. And because I'm geologist, you say that black sand. So black sand, I want to know something. Why the sand is black? Is it the shale mixed sand? I don't know why. So I want to know why the sand is black. Okay, thank you.
Thank you very much for your kind words, and you can tell me that next time I will do much better. I just know about it in 2 days and I was in it. But coming to black sand, it's heavy minerals with a very high density, and it's really black. And even to prospect it will be very easy. You come along the beach, you will see on the top or some at a different level, with having the sand, white sand on top, buried, and again with another generation, 50 centimeters on the top, with very thin layers, and again. But usually, what people harvest is the first meters and on the top. It comes on the top. You just have to follow it. You cannot miss it. You will see it. Absolutely black in color. And the two minerals are ilmenite or rutile. And one of the characteristics is you can make the separation by electromagnetism. It's very magnetic. Very
here in Brazil,
Kaiser is saying that it's coming from Brazil, but it's coming from the rocks nearby, and we've I've been washed by the waves, and it brings it from the sea to the surface.
I'm saying that Brazil has a lot of.
yes, here in Brazil we have some,
Yes.
we have black sand.
Do you exploit it?
We dominate, yes, Bahia State and other states.
Here in Rio de Janeiro,
Because
Here,
the
Rio de Janeiro.
exploitation of this sand, Paraíba. Okay, I have a question for you.
Tell me, is it because of oil that you don't exploit it anymore? Is it because of the oil you don't exploit it?
I have a question for you, Professor. You mentioned about the sand, the black sand that we call placer. You know, have minerals, and we know that one of the use of this sand is for industry, like titanite, another chemical element. But you mentioned about another use that I have a curiosity. You mentioned about to paint with sand black with this sand. Can you explain, please?
Most of the time, the painting you see on the road when you are driving with a very high reflection is made from. If you don't have the titanium oxide, you will not have this result. It's very much used for the painting, again for the industry.
Any question?
Good afternoon. I have one question for Dr. Baidi. Congratulations for your presentation. And I would like to ask you about you have some information about the situation of the delineation of the EEZ of your country, Senegal, and some other countries in the Africa.
Thank you very much. And first of all, in the first study, we know that we can claim, as a presentation which was done by the president of the the limit of the continental shelf, we know that we have a claim. That means that in the southern, after Gambia, to the south, we can go up to 350. That was given to us by the first study. That was the first result. We know also that some African countries are very much in advance, like South Africa. They have started since a long time, but even they have not yet given doing their submission. I know that some countries from the southern part are advanced, but Namibia, but most of the countries may have some delay. I know that the chairman said yesterday, one has to submit a claim. Even the study will be very preliminary, but it will not be under consideration until you give your full and complete submission. And I know that many African countries was about to say if the deadline of May 2009 can be extended, but the will was not to expand it, but to find a kind of medium interim solution. If even people realize, that is the lawyers, that all submissions have to be deposited before the date, even incomplete. Legally, no one can come to you or reject your claim at a further stage. So the door is still open. And I think most of the African are all, and that is the situation also in all the developing countries, same situation more or less, that people will use very much the decision taken last year in the sales parties meeting. Thank you.
Okay, Mr. Roberto Tudor, if you have a message, please use the microphone.
I only have a brief announcement. Well, for those of you that are going to go to the summit today, the van will leave by 8:30. And the reason for that is that for those of you that are in this hotel, we have a voucher for dinner. And dinner starts at 7:30. And for those of you that is in the hotel, can pick up your voucher with Michelle. Michelle is a nice lady that's just outside and help us do everything we need. So I'd like you to pick up the voucher for dinner tonight. Okay? Thank you very much.
Okay. That's the end. Thank you very much.
Good morning. I think we should start now for our last day of the seminar. And I would like to invite Mr. Jose Lima to be the chairman of the session. And I'd like to have some announcement too. For those that will leave the hotel today, we should leave by 1:30, not after that. So for those that are leaving today Rio, they should also leave the rooms in the hotel by 1:30 today. Okay, thank you very much.
Good morning. It's a pleasure having you all here today. Thank you for coming. This is a very important subject to Brazil, not only for Brazil, but all countries are interested in this subject. So Brazil is putting, the Brazilian government is putting a lot of emphasis on this subject, and the reasons you all know. And as you also know, we have a methodology that we will follow, similar to the other days. We will have two presentations, and we will start with a friend of mine, colleague from Petrobras. James Miller will present on gas hydrates. And following the structure that we already have during the seminar, the questions will be made at the end of the second presentation. So let us see the presentation, see the second presentation, and at the end of that, we'll have some time to make some questions, make some comments before we go to the coffee break. Thank you. Dennis, please.
Good morning. My name is Dennis Miller. I'm a geologist. I work for Petrobras at the R&D Center here at Rio de Janeiro. Today I will present to you gas hydrates in the Brazilian continental margin, inferred occurrences, and current investigations. My presentation will be, the outline is first a definition of what gas hydrates are, characteristics of the gas hydrates, associated features and seismic records, mainly BSRs, potential as energy source, inferred occurrences in Brazil, and I've got a couple of slides from Africa as well, current investigations in Brazil, and conclusions. Well, gas hydrates, what are gas hydrates? They're compounds occurring in nature as crystalline solids in the form of ice, where gas molecules that act as guests are trapped by a lattice of water molecules that act as hosts, forming cage-like structures known as clathrates. So these are the capillary structures here, cage-like water molecules form a cage-like structure, and in the center we have the gas molecules, which are gas molecules. So this structure is called a clathrate, and gas hydrates are a type of clathrate. So a lot of people use clathrates and gas hydrates as synonyms, but they're not necessarily synonyms. Hydrates are a type of clathrate. Common examples are methane hydrates and CO2 hydrates. So in those cases, the molecules inside the cages are methane and CO2, but we can have other gases as well inside the structure. They're found in nature below the permafrost in polar regions, as you can see on the map here. The polar regions here in the northern pole, and mainly Siberia and Canada, and perhaps there should be a lot also in the Antarctic. And in marine or lacustrine sediments and water depths generally exceeding 400 to 500 meters. The gas hydrates occur in 3 different chemical structures: structure 1, structure 2, and structure H. This is the general scheme of the chemical structures of all 3 of them. And this is a diagram from Sloan, where we have a single cage with a molecule inside, and structure 1 has 2 different cages and forms this crystal structure. Structure 2 has 2 different cages also, but the second cage is larger than in the case of structure 1, so it can have propane as a gas, isobutane, natural gas, whereas structure 1 can have methane, ethane, or carbon dioxide. And we also have structure H that has 3 different cages, and the third one is large enough to have 2 gas molecules, sometimes methane and neohexane. Going on to the characteristics, conditions for formation. This is important, we all understand this. Gas hydrates, they require specific conditions for their formation. And those conditions are high pressure, low temperature, high gas concentration. This is very important because a lot of people don't put emphasis on a high gas concentration. You have to have gas to have gas hydrates. Here we have a phase diagram, a phase stability diagram, and a hypothetical case of seafloor at 1,200 meters in water depth. So this is the diagram. We have on the y-axis the depth, which it's equivalent to the pressure, and the temperature on the x-axis. We have the seafloor at 1,200 meters. The yellow part of the graph is a hydrate stability zone. This curve is a gradient of the temperature of the seafloor, and this is the geothermal gradient. So when the temperature of the seawater reaches around 450 meters, you have conditions of forming gas hydrates if you have sufficient gas concentration. In this case, when the seafloor is 1,200 meters and you have gas concentration, you have a gas hydrate stability zone, which will be, the thickness will depend on the geothermal gradient. The higher the geothermal gradient, the shallower it will be. And the lower the geothermal gradient, the thicker it will be, the deeper it will be. So the gas hydrate will dissociate from the water once these conditions are not met. When the temperatures exceed, in this case, between 10 and 20 degrees, or when you release pressure. So in this case, you have probably a dissociation by both pressure release and temperature, and here the gas is dissociating and burning. Characteristics, different morphologies. They have found different morphologies in gas hydrates. Some examples are shown here. First one is filling oblique and subvertical fractures in muddy sediments, and this is quite common. You see here, this is a tomography image, and the white fractures here are filled with gas hydrates. The length of the core is 90 centimeters, and here we have some sections. Over here you can see how complex the fracture pattern is. Another form of occurrence, another morphology would be by nodules, lenses, layers or laminations in muddy sediments, or disseminated in sands. And these are the type of deposits that today are being tested. Types of deposits. Walsh classifies gas hydrates deposits into 4 types. Type 1, hydrate deposits over free gas zones. Type 2, hydrate deposits over water zones. Type 3, hydrate deposits over no mobile fluids that would be inside the gas hydrate stability zone at isolated lenses. And type 4, localized and dispersed deposits on the seafloor, which are quite common in places like in the Gulf of Mexico. Only types 1 and 2 are explodable with the current technology. So current technology cannot extract gas hydrates from these type 3 and type 4. Potential uses of gas hydrates as an energy source, as gas storage and transport, geologic storage of CO2, where the idea is to inject CO2 into the reservoir, and the CO2 will substitute the methane molecule, and you will keep your hydrate in the formation. You will produce methane. The idea is being already done experimentally in laboratory. Another use is hydrogen storage, seawater desalinization, and refrigerating systems. Associated feature in seismic records. The occurrence of gas hydrates is generally associated to specific features in seismic sections. And that's how we identify the possibility of having gas hydrates in geologic settings. BSRs, which are bottom simulating reflectors, are considered the most diagnostic. And I'll explain to you why they form, why they show in seismic records. This is a diagram from Planell in 2000. We have different curves here. This is the hydrate stability curve. This is the gradient, the temperature gradient on the seafloor and on the soil, the sediment. And this is the seismic velocity. Okay, we have a constant seismic velocity which enters the seafloor and increases. The seismic velocity increases due to density increase. And then when it reaches the bottom of the hydrostability zone with a free gas zone in the bottom, the velocity just decreases abruptly. And we have a decrease in density as well. So what that turns out to be a difference in acoustic impedance, which causes the BSR to form. As you can see here, the grains are surrounded by water and hydrate, and the free gas zone is gas and water. So you have a density and a velocity contrast. And that's why we get a reflector here called BSR simulating the seafloor. Other related features are gas chimneys, acoustic blanking and turbidity, high amplitude reflectors, mounds, elevations on the seafloor, pockmarks, which are depressions on the seafloor, and acoustic plumes, which are plumes inside the water column. Here's an example of a seismic section from the Canadian continental margin displaying the BSR. It would be this reflector mimicking the seafloor. Some comments regarding the BSRs as a diagnostic tool for gas hydrates. Gas hydrates are not always present when BSRs are observed in seismic records. So in some cases, where you drill where the BSR is, you don't find gas hydrates. Another possibility, gas hydrates can be present where BSRs are weak or absent. So in this case, where it's the BSR is absent or weak, sometimes you do find gas hydrates in those places. And Barrett and colleagues have shown that similar BSR features that look like these BSRs, can also occur where diagenic transformations from opal C to opal AT and from smectite to illite have taken place, and where large amounts of alphagenic carbonate have been deposited. So BSRs can be something else than gas hydrates. So the potential energy source, according to Sloan, the great energy potential of gas hydrate derives from the fact that one volume of gas hydrates with total occupancy of gas cavities corresponds to 180 volumes of gas at surface. So you multiply your volumes that you have in a gas hydrate by 180, and that's how much you would have at surface. Some authors estimate that gas hydrates may contain more than twice the amount of energy than all other fossil fuels combined. That's what these authors say. However, recent estimates indicate varying recoverable volumes depending on the type of reservoir and the geologic setting where it occurs. And this is where these pyramids come in by Boswell and Collett. And this would be the total volume estimated of gas hydrate and all other gas resources. The three upper layers here in this pyramid, which is developing or proven reserves of all other gas resources, would probably be equivalent to these first three layers here, which are Arctic sandstones, under existing infrastructure or Arctic sandstones away from infrastructure, or deep water sandstones. So this volume probably corresponds to this volume, and this is what we can probably extract nowadays with the technology available. So with the technology, we probably have something, we would double the amount of gas that we have available today as far as the resource is concerned. So I don't know if it would be the double of all fossil fuels. It would be 1 times more what we have here as gas and other resources. Production from permafrost, production tests carried out in Malik, 2L38 and Malik, 5L38 wells in northwest Canada. This was done by a consortium between Canadians, Japanese, Americans, I believe Germans also. They performed the test on these 2 wells, and the test was done using depressurization. This is a well test assembly. The reservoir would be around here, around 30 meters in thickness. And what they did, they placed a pump here where the reservoir was, and they pumped the water out of the well, so they took out the pressure, the hydrostatic pressure from the well. And that meant that the hydrates dissociated and were produced. The test, there were 2 tests, one in 2007 that produced 130 cubic meters in 15 hours. And the test in 2008 was 140 cubic meters in nearly 6 days. So this is not a very significant production when compared to conventional gas wells. Production from deep water sands, the ones that are the country that's probably the closest to producing deep water sands is Japan. The production tests are expected within the next 5 years in deep water turbidite sands in the Nankai Trough, east of Japan. The in-place gas volumes are estimated to be 20 TCFs. They have already drilled, I believe, about 12 or 13 wells in Nankai Trough. So they have a very good control of where the hydrates are and how they occur. So this is a pretty good estimate, 20 TCFs for that specific deposit. So what are the challenges? The challenges, first, is a slow dissociation, relatively low production. So in the hydrocarbon industry, we're used to producing fluids in the reservoir, either in the gas or the liquid state. Gas hydrates are in the solid state in the reservoir, so you have to dissociate them. And they dissociate rather slowly. Well, significant water and sand or mud production from relatively unconsolidated reservoirs. As you produce, there's a lot of sand being produced and mud. So you have to take care of that. Either displace it or inject it in another well. Another fact is the horizontal dissociation front. Horizontal wells are not as effective. In normal hydrocarbon reservoirs, hydrocarbon wells are very effective to increase production. Some authors claim that in gas hydrates, the dissociation front is horizontal. It doesn't go vertically. So it doesn't make much of a difference if you're producing from a horizontal well or a vertical well, according to some authors. Secondary hydrate formation in the well and production lines. The hydrate may form again once it's dissociated. It might form again, it might crystallize again inside the well or in production lines. Well instability, we're producing from a reservoir, a rather inconsolidated reservoir, and we're producing part of the reservoir as well, so you can have a well instability. And overburden collapse. You're also taking some part of the reservoir, the overburden might collapse. So these are the inferred occurrences in Brazil that we know until now. The first one I'm going to mention is the Rio Grande cone, which is down the southern tip of Brazil, and the Pelotas Basin. The estimated area is 45,000 square kilometers within the vicinities from 500 through 3,500 meters, and an estimated volume of 780 TCFs. If you remember correctly, the Nankai Trough is 20. So this might be a little bit overestimated. Some seismic lines showing some features. This is the ESR, okay, following the seafloor. in the upper to middle continental slope and the Rio Grande cone. As you can see here, there's a lot of what we call gas chimneys that may be actually faults that are reaching all the way to the seafloor and running through the BSR. Another section here going down to the mid or lower continental slope. It's a very noticeable BSR. You see that in the seismic record we have a frequency change from above and below the BSR, a lower frequency below the BSR, and amplitudes are a little bit greater also below the BSR. Now another seismic section on the continental rise below the thrust and fold belt. We see the BSR following the seafloor as well, and this is in water depths of around 3,000 meters. So we do have BSRs in deeper portions of the basin as well. Now I'll mention the Amazon cone occurrence. At the Foz Amazona Basin, the area is 28,000 square kilometers with symmetries from 600 to 2,800. Estimated volume 430 TCFs. This is being remapped by some groups here in Brazil, and it seems like the area is a little bit larger than this. But this volume, again, it may be overestimated. Seismic records from the Amazon cone. This is on the thrust and fold belt, and we can see a reflector cutting all the normal stratification. This is the BSR where we suspect there might be gas hydrates. Another section from the thrust and fold belt. This reflector right here is interpreted as a BSR. Another cross-section on the thrust and fold belt, a very straight BSR following the seafloor. And other BSRs along the Brazilian continental margin that we have in other basins, a little deeper. This is around probably 500 to 600 meters, and another quite clear one down here. Well, other areas in the Brazilian continental margin to be investigated for gas hydrate accumulations. This would be the model that we could follow to investigate gas hydrates in these settings. These are deltas, prograding deltas on the coast, the continental shelf, the slope and the rise, and these deltas, they may prograde into canyons that feed into a fan or cone. And exactly in these fan or cones, just like in the Amazon cone, that's where we could look for gas hydrates if we're looking for biogenic gas hydrates. If we're looking for thermal